Hello, thanks so much for organizing this and inviting me. So I'm going to talk about some very old and some very much newer work in this subject. So as many of you know, AI goes way back. This was the proposal written by McCarthy, Minsky et al. For the AI summer workshop at Dartmouth, and that took place in 1956. And here was their goal. And note that here, one of the goals was to form abstractions and concepts. What does that mean exactly? It seemed to be, very important, right next to language and improving themselves. So, but more recently, we've seen this rise of deep neural nets. This is just a convolutional network picture that has given rise to a real revolution in AI. I think most people are familiar with the ImageNet competition, which was maybe one of the first big things to happen in deep learning. More recently, it's where there's big data. 1.2 million images seems small compared to the things that, say, ChatGPT is trained on, but it was big at the time. And there was a competition to recognize images. Every year, this is the error rate of the best program. Back in the 2011 and 2012, the beginning was 2012, the best programs were based on an architecture called support vector machines, which is a sort of old machine learning architecture. And you can see they're getting about over 25% error rate. But suddenly in the end of 2012, this thing called supervision, which was the also now known as AlexNet, was submitted. It was a deep convolutional neural network and really made a big drop in the error rate, shocking to people at the ImageNet competition, the people who were made this data set themselves, that something like that could actually work. And this was, of course, now the progression of deep neural networks getting deeper and deeper, meaning there are more and more layers, more and more parameters, until finally 2017 was the last time I think this competition was run. The best neural network was now below the error rate of approximately what was tested as human performance on this. Okay, so deep learning, really great, really important. But what are these machines learning? That's a big question, because they're very deep neural networks with lots of parameters, and it's hard to figure out what they're learning. But people found that even though they were doing extremely well on this big ImageNet data set, they had some issues with out of sample kind of data. So here's a picture of a fire truck, kind of simulated picture that a neural network trained on ImageNet recognizes with 99% confidence. But this paper, which was in 2018, showed that if the fire truck was, and then they were using photoshopped into a different pose, now the network's 98% certain it's a school bus or a fireboat or a bobsled. That one I like. So this is showing sort of the what people call the brittleness of these networks. They do extremely well on data that's similar to what they've been trained on, but they had strange failure modes for things that were sort of outside the distribution of their training. And you might say that what these networks have learned is perceptual categories. That is, they've taken this giant multidimensional space of categories, which is, ImageNet has 1,000 object categories. They've divided it up using multidimensional hyperplanes. And they've learned this way of classifying all the different possible things, but they haven't learned what we might call robust, rich, human-like concepts. So here's a little example of what we might mean by a robust concept. So you could imagine the notion of a bridge. And you might, the network might learn from lots of pictures of bridges that, you know, some kind of statistical description of what a bridge is, and it would involve some kind of structure going over water. But we humans are much more flexible. We can interpret lots of things as bridges that are far from that. So here's I think this is in the Netherlands somewhere. It's an aqueduct or a water bridge where instead of cars going across or people going across water, it's boats going across land or a road through water. So it's sort of the inversion of a bridge. It's very, you know, it is a kind of abstract bridge. You know, ants forming a bridge with their bodies, people bridging their hands, the bridge of your nose, you know, the bridge of a song. All these things are abstractions of this very general notion that we have. And it can go on and on. You know, we talk more abstractly about bridging the gender gap. Biden, when he was running for office initially in 2020, he said he was going to be a bridge to a new generation of leaders. Unfortunately, that didn't work. But you can imagine this notion of being a very abstract notion of a bridge. And it just goes on, you know, and this isn't special to bridge. Many, maybe most words can be abstracted in this way. So Larry Barsalou, who's a cognitive psychologist, defined a concept as a competence or disposition for generating infinite conceptualizations of a category, which I like this because it's a notion that a concept is not just, you know, a sub part of conceptual space, but it's a generative model. It's a generative, it can generate all these different notions of bridges and whatever else. So the concept gives us this generative property in a very flexible and rich way. Hofstadter, who you heard about, who felt that analogy is the core of cognition, defined a concept as a package of analogies. And you can imagine that the bridge example, you know, all of these things are in some sense analogies. We're mapping the essence of a concept into different instantiations. And they can be very concrete or very abstract. So in this talk, and I don't have the time, but hopefully, can you tell me when it's like 5 minutes? Yeah. Okay. I'm trying to figure out how to get machines to learn concepts rather than perceptual categories and make analogies. And then also how we can evaluate the degree to which a machine has a general capability for robust analogy making. So back in the late 80s, early 90s, I worked with Hofstadter on analogy making. Here's my book that I turned my PhD dissertation into. It's called Analogy Making as Perception, because the idea is we were building a model that in which it was a notion of high-level perception, not tied to any particular perceptual modality, but the idea that in your mind's eye, you are making sense of a situation via analogy to another situation. And our model had inspiration from different aspects of neuroscience, psychophysics, psychology, the idea that you have kind of a mind's eye. This is a work from some neuroscientists who said that the V1 and V2 areas of the visual cortex might act as what they called active blackboards that are sort of doing computations that represent perceptual data that is available to other parts of areas. And Kahneman, Treisman, and Gibbs had this notion of object files, where you can have on these sort of blackboards, these temporary modifiable perceptual structures that are made on the fly. And Mandler, another cognitive and developmental psychologist, who said there's actually a continual interaction between perception and concepts, that the perceptual system is you interpret these things conceptually, a bridge or chair or what have you, but the conceptual system also determines what gets perceptually processed. My expectations, the concepts that I know, I'm constantly trying to use those in trying to understand what I'm perceptually perceiving. And we were also inspired by Shimon Ullman's work on visual routines, where vision is a set of sequences of basic operations that are wired into the visual system and composed. So I'll show you how all of those inspirations give rise to our model. So our model was very different from, say, a neural net or a transformer or any of the things that people use now. It was much more dynamic. It wasn't a feed forward process. It was really a dynamical system in which perceptual structures were created via the moment-to-moment composition of visual routines in which concepts were influencing and were in turn influenced. So let me just give you an idea of the architecture of this system. The idea of the mind's eye, the blackboard, we call the workspace. And we used as our sort of the fruit fly of analogy was these letter string analogies. That is, they were our little idealized model of what analogies are in general. So we have these situations, these strings of letters that have objects, they have relationships between objects, they have events that happen, something changes. And then, so you can think of the top row as some sort of dynamic situation, in which something's changed. And now we have the bottom row, which is a different situation. Now do the same thing to this situation. And Hofstadter came up with this domain, and it seems very simple on the surface, and yet it's incredibly open-ended. We developed thousands and thousands of such problems that explore all kinds of different kinds of analogies in this little letter string world. We also have a network of concepts that interacts with the workspace. So the idea that perception and in the mind's eye and concepts interact. And that concept network consisted of different concepts in this world of letter strings, but you can imagine them being extended to concepts in more complex domains. So we have things like the letters of the alphabet and the knowledge about successorship and predecessorship, rightmost and leftmost letter in a string, successor and predecessor in a string, first and last in the alphabet, and other concepts that are connected and can, once these concepts can get activated, they can then in turn influence what happens in the workspace. Okay, and remember the idea of visual routines. In our world, these were perceptual agents, or what we call codelets, little pieces of code that were experts on doing specific things like finding successors or finding mappings between the two strings. They were really, each one reflected a concept in the concept network. So I'm going to actually just skip ahead here and show you, oops, I didn't want to start that so fast. Stop. Let's go back. Okay, so I'm going to show you a demo of the program running. Okay, so here you see the workspace. You don't see the concept network, but what you're going to see is these little visual routines or codelets coming in and making hypotheses. So the goal of the program now is it's faced with this problem. I don't know, can you see this in the back? Okay, it was faced with this problem of trying to figure out or build a representation of what is happening in the top row and then map that representation onto the bottom row. And all it has is the concepts. It's not learning anything. It's trying to apply the concept it has to every new problem that it's faced with. And so you're going to see this sort of dynamic composition of concepts to create an understanding. These are all like little hypotheses. If the hypothesis, like that B, the B and the B are the same letter, pans out, it draws a little dotted line. The sort of thickness of the line is related to how strong the concept seems right now. And note that, I'll stop it for a second. There's this temperature. So this is a measure of how close the system feels it is to a solution. Starts at 100, it's a centigrade scale. It starts at 100, goes to 0. So 100, it's maximally confused. At 0, it's maximally happy. And it reflects the strength of the structure and the coherence of the structures. But it also has a feedback effect. The higher the temperature, the more randomness is injected into the system. It's like in physical system. And as the temperature goes down, the system becomes more and more frozen into a particular point of view. So you can imagine when you're faced with a problem, you don't really know how to solve it. You're thinking of all different kinds of things. One of them seems to be promising, so you then start to focus on that. But you're also sort of in the background considering other possibilities. But as you get closer and closer to a solution, you are sort of freezing in on a particular point of view. And sometimes that point of view doesn't actually work out, and suddenly the temperature will go back up again. And you'll say, uh-oh, I better rethink this. So I'll just let this run. You can kind of get an impressionistic view. It's trying to map the structures here to the structures here. And you can see these structures are built and are broken, but now it's freezing in on a solution. And here it says, reverse the direction of the string. And here it says, reverse the direction of the whole group. So what it's doing is reversing the direction of these groups. So it's mapping letters into groups. And so this program was able to solve many letter string analogies in this very dynamical way. It's kind of a mixture between a symbolic and a sub-symbolic AI system, because we have these symbolic concepts like rightmost, leftmost, but they actually have, they're not atomic. They can have a gradation of importance or salience at any given time. And we also have these sort of numerical notions of randomness or determinism in the system. Yeah.
Is it okay to ask a question?
Yeah, go ahead.
So there must be some kind of energy measurement going on.
Yeah. Yeah.
Can you give a little bit of details what this energy is?
Yeah, so the energy or the temperature is computed. We have all these perceptual structures like these. We have these relationships, we have these groupings. Every time there's some structure built that has an effect on the temperature, it lowers it. And the more coherent the structures are, like this is a little group of 2 identical letters, and we have 3 of those. That seems promising. That lowers the temperature more. So it's really a measure of how good this structuring is. So that's sort of I mean, it's a little bit ad hoc, the way that it's computed, but that's what it's meant to measure. Sorry? How is it computed? Well, I can't give you I'm not going to give you the like equation for it, but because it's kind of complicated, but it's sort of a sum of the strengths of these structures that's normalized. And the strengths of these structures have intrinsic value, and they like a letter going to a letter is very strong. A letter going to a group is a little less strong because there's what we call a slippage. A group like this is very strong. A group like this is very strong. In some cases, we saw like there was a hypothesis that C should map onto P. That was less strong. This is the rightmost and this is the leftmost. So anyway, there's kind of a set of factors that go into computing it.
Could you think of those as sort of hyperparameters of the algorithm?
Yeah, it's kind of a hyperparameter of the algorithm, right? You can define it in different ways. Yeah. Okay. So just to go over once again, the important ideas, we're trying to model analogy making and other kind of high level cognitive processes as in a way analogous to perception. All these dynamic things are going on, except they're in your mind's eye. A representation is actively built over time, and it's dynamic. Perception is dynamic. You move your eyes around, and the same thing in your mind's eye. You're continually integrating sort of top-down expectations from concepts with bottom-up processes. And by the way, if you're taking notes, I'm happy to share these slides if that would be useful. I'm not sure how we would do that, but
it's also recorded and will be available.
Okay. And I don't know if you noticed, but we have this. We didn't program this in, so we call this emergent. The program starts out being very bottom up. Lots of different things are being tried. There's not much influence from prior concepts. They're all sort of equally likely to be tried. But as the temperature decreases and the system gets more organized in its representation of what's going on, the system becomes less random, more deterministic. It's more attentive, meaning that certain kinds of concepts are going to be focused on. And this is also seen in human perception, this kind of emergent transition. This is something that the psychologist Anne Treisman studied, how we transition from sort of a random bottom-up kind of processing to a more focused, attentive kind of processing. Okay, so now let's jump ahead. So this is stuff I did back in the 80s and 90s, a long time ago. The, middle age, I would say the prehistory of AI. So most people, like a lot of people, you ask them, when did AI begin? They're like, oh, about 2010, But in 2023, this group from UCLA, many people will be familiar with Keith Holyoke, who's been working in analogy for decades. They claimed that they discovered that large language models, in their case GPT-3 at the time, had emergent capabilities for analogical reasoning. Okay, and this got a lot of press. Undergrads get beaten on questions like those that help them get into college. All right, so they claimed, so they used these letter string analogy problems as part of their study. And they also used a couple of other domains, what they call digit matrix problems. So if you're familiar with Raven's matrix problems, I don't know, some people here probably are. The idea is that here we have some pattern along the columns and along the rows, and you just have to fill in the blank. Okay, pretty simple, right? And these can get, they can use multiple numbers and different kinds of patterns. Okay, so they used those. They also used these story analogies from a study by Dedry Gettner et al. So you have a little story. I don't know if you can see this, but it's like a little fable. And then there's two target stories, one of which is sort of superficially similar to the original story, and one of which is more causally similar, that it is the sort of the better analogy. So here, it's story A was the better analogy. So you don't have to like read these in detail, but I'll talk a little bit more of them in a minute. So this is, in their work, they found that they gave these problems 0 shot to humans and GPT-3, which is a precursor to ChatGPT. And 0 shot means that you don't like give it examples before you test them. And they looked at GPT-3 accuracy and humans, how well they did. Okay, so it's a little bit subjective, you could say, because it's not like these problems they're not like math problems that have a real, true, correct answer. The answers kind of make your judgment about what the right answer is. But they made judgment about what the right answer was for each problem, and they showed that GPT-3 was better than average UCLA undergraduates. Although some of the UCLA undergraduates were perfect. Okay. And similar on the digit matrix problems. And humans were better on average on the story problems, but the GPT-3 system was still not bad. It was better than sort of random guessing. Okay, and GPT-4, as you can imagine, was even better. Okay, and oops, can't see this, but it says, our results indicate that GPT-3 displays a capacity for 0 shot analogical reasoning across a broad range of tasks. Okay, so we read this paper in my group and we were curious about, like, wow, how good are these systems really? And so at the time, Martha, where are you, Martha? Martha Lewis was visiting my institute, and she and I worked together on working on saying, how robust is this really? And so this is a paper we published this year in this journal, Transactions on Machine Learning Research. And here's what we did. We said, and this is part of a kind of a series of papers that lots of people have worked on testing the robustness of claims about analogy and other kinds of reasoning in large language models. The idea is that if they can do well on one kind of benchmark, they should be, if they are general and robust, they should be able to do well on versions of the problems in that benchmark that are less similar to what they've seen in the training data. Okay, so we tried 2 different variations on these letter string problems that you should be able to do if you can do these very generally. One is we swap some letters in the alphabet. We say, use the following alphabet to guess the missing piece. So I should say, if like we're using problems like ABC changes to ABD, what does PQR change to? And these LLMs are trained on predict the next token, right? That's what they do. And so we're saying predict the next token. So they're not bad at that. But here, the next token might be out of order in a weird, in the usual alphabet that you've been trained on. So this says use the following alphabet, and here, in this one, M and E are swapped. Okay, and then we give a problem, so this is kind of a counterfactual. Pretend that the world is such that the alphabet looks like that. Now, solve this analogy problem with the alphabet that looks like that. And here, M is playing the role of E. And so you have to make that flip. We also did another kind of variation where instead of letters, we use symbols. But we said, here's the ordering of the symbols. Use that. Okay, so it's maybe a little harder, but presumably if you're good at one kind of analogy, you should be able to adapt to this. And here's what we found. So the x-axis is the number of letters that were permuted in our counterfactual alphabet. And for each counterfactual alphabet, we produce lots of variations of them. And here's the symbol alphabet. The blue dots are human performance. We tested humans on the Prolific platform. And we tested GPT 3, 3.5, and 4. And you can see that here we actually found something different from the original paper, which is that humans on our test did better than GPT-3 as opposed to what they found. But the interesting thing here is that while humans stay pretty constant, they go down a little bit, the GPT models go down a lot, especially for symbols. They just cannot adapt these things that are so different from what they've been trained on. We also looked at examples of variations on digit matrix problems. And here are the types of variations we did. One is, instead of having the blank square where the answer goes at the bottom of the matrix, have it at a random place. Yeah.
I had a question about some slide.
Read this slide.
One more? Yes, that's fine. Thank you. I guess that use the following alphabet, there's the list of these and so on. Was the prompt used in GPT?
Yes. This was a good thing we gave to humans, and we gave something almost identical to GPT.
Yeah, I'm thinking because the word alphabet.
Yeah.
Because alphabet has sort of meaning.
Yeah.
Did you also try maybe other word like word sequence or?
No, we didn't. We didn't.
We did try a bunch of different prompts. We tried like 3 or 4 different prompts, which chose the one that gave the best.
Yeah. Yeah.
I have a related question. Do you consider the effect of tokenization that we have on this?
Yeah. We put spaces in.
Does that force the tokenizer?
It forces it tokenized, and we actually did some tests. We did some tests to see if it understood the problem. So we said, what's the successor of A? What's the successor of B? And so on. What's the successor of M in this world? And it was able to solve those. Yeah. Yeah.
Some question, but what we know is we did the names for all the tokens. If you swap the actual vector that generates each letter, then you will swap the token that is for the right letters.
Yeah.
You have a.
I don't know. I mean, you can't do that in GPT-3 for one thing, because we don't have access to the embeddings. Yeah, so we didn't try that, but what we were trying to do is give something as similar to the experiment of the original paper as possible. Yeah, so we're just giving some of this, their claim, so we're not saying necessarily GPT-3, GPT-4 can't do this with some kind of special prompt or we're saying, we're looking at their claim, which is 0 shot with these kinds of prompts, emergent, analogy capability. So, okay, so now the digit matrix problems, we tried that kind of variant. We also use symbols instead of digits. Okay. And what we found is that here's the original. Again, blue is humans, and these are GPT 3.5 and 4. We didn't have access. They got rid of GPT-3 by that time, so we didn't have access to it. And you can see for a random answer position, humans have no problem with that. But the GPT models had a huge amount of problem with that. Because I think because they've been trained, and the other thing is we did test them. We said, where should the answer go? We didn't ask them what the answer was. We said, where should the answer go? And it was able to tell us what position in the matrix the answer should go in, but it couldn't somehow form the answer very well. On the simple task, it did. Both humans and the GPT models had no problem. They both did just as well. And on the story problems, we did two kinds of studies. One is that if you look, we noticed these were used on humans back in the 80s by Gentner et al. And we noticed that there's kind of what you might call a shortcut solving the problem without doing the analogy, is that the correct story, here's the source, the correct story typically was superficially more similar than the incorrect story, in that it had almost the same number of sentences. Here you can see example 6. There's always this last sentence, which is irrelevant. And the sentences had often had syntactic similarity. They used synonyms like naturally, needless to say, this is rather disappointing, she became somewhat disappointment, and that was lacking here. So it was possible to do well on this task without being able to do analogy. So we tested this by paraphrasing the correct answer so that it did not have this, it still contained the causal analogy, but it didn't have this syntactic similarity. Okay. And what we found, so here is the accuracy on the original stories. GPT-4 did better than people originally, but when the stories were paraphrased, both GPT-4 and humans went down in accuracy, which means possibly that both humans and GPT-4 were using these shortcuts, exploiting these shortcuts. GPT-4 went down a lot more. The numbers are not quite large enough for our number of samples to say anything definitive, but this is suggestive that these shortcuts were being used. And the other question we had was, does the answer order matter? Shouldn't matter, right? Multiple choice shouldn't matter. But we noticed in the data from the original paper that actually it was much more likely to get it correct when the correct story was listed first. So it did have a kind of bias. And we repeated that experiment and we found, look at humans first. This is the correct answer was listed first. The correct answer was listed second. And you can see humans, there's no difference, but the GPT model had a pretty big difference. So it had a bias towards order. And all of this indicates that there's some question about the robustness of these results. And in general, and I don't have time to talk about all the many studies that show this, but it's known that LLMs are much better on solving reasoning problems that are similar to those seen in the training data or that allow shortcuts. Okay, now we now have new kinds of models that are trained explicitly to do quote unquote reasoning, right? We have O1, O3, DeepSeek R1, all these things. I don't know if you all have heard of these, but they're different from like the GPT models in that they are explicitly trained to kind of produce this, what they call a chain of thought. And seem to be better on reasoning. We haven't tested those. Martha might be working on this. Yeah. Claire's tested them.
They make exactly the same mistakes as the earlier model.
Okay. Interesting. Okay. Yeah.
I just have a question, if you actually have to generate, you know,
If to generate the analogies, what do you mean?
they generate their own stories.
Oh, I haven't tried that.
Model, right? So it's about reasoning versus generation.
Yeah, I haven't tried that, but there is a really good paper about that kind of thing, where they ask the model to generate a story about something and it generates it. And then they ask it some questions about the story, and it's quite bad at answering the questions. So the paper is called something like generation and understanding, and they're not the same thing.
Thinking about the analogy test, that is roughly together.
Yeah, good question. Something to try. So how can we get machines to learn and use human-like concepts and abstractions? Well, I think that this work that we did on copycat with the letter string analogy model back in the 90s actually is quite promising and something that I'm working on now, possibly integrating some aspect of neural networks that can help make sense of more complex domains, and having a kind of hybrid system that actually does the more dynamical part. How much time do I have?
10 minutes.
I have 10 minutes? You
Yeah.
sure?
Then we even have time for questions. So,
Yeah, I want to leave time for more
yeah,
questions.
yeah.
Okay. So let me skip now to some interesting work on this abstraction and reasoning corpus. How many people have heard of this? Okay, not everybody, a few people. So this is a more recent set of analogy puzzles that were created by Francois Cholet, who was at Google. He now has a startup company to work on solving these. Okay, and they were inspired by what are called core knowledge systems. This is a theory in psychology that's a number of people have promoted, especially Elizabeth Spelke and Susan Carey, both at Harvard, that the idea that concept learning builds on innate or very early learned systems of knowledge, such that things like the world is divided into objects, and certain objects have certain kinds of interaction properties, or persistence properties over motion and things like that. Notions of numerosity, such as one set is greater than another set, or something's bigger than something else. Basic geometry and topology, things like something being inside something versus being outside. And also the notion that some things in the world are agents that have goal-directed behavior, and some things are inanimate or not goal-directed. So this is kind of a theory that a lot of controversy about whether this is really innate or learned, or whether this actually, what are the core knowledge systems, but this is what inspired Cholet. And so here's an example of one of his problems, he calls them tasks. The idea is that it's sort of like the copycat letter strings, except they're two-dimensional colored grids, and there's more examples. So here's what he calls a task demonstration. You have a grid that transforms into another grid. Here's another example. Here's another example. So I've given you 3 training examples. And now here's the test example. And you have to do the same thing. Okay, so that's not hard, right? and this involves like recognizing objects, recognizing spatial concepts like extending something to a border, color sameness, the color of the thing you extend is the same color here. If you show this to a kid, they'll say, oh, it's a laser gun or something like that. So we bring in our own like human cultural concepts, but presumably Cholet's theory was all you need are these core knowledge systems as your prior concepts. Here's another task. Anyone see what the answer is here? Okay, what is it?
L shapes are called U shapes.
So it's shape invariance. And we have names for these shapes, like you said, L, U, and H, but you can still think of them even without names for them. You probably could do it. Okay, so Cholet created 1,000 tasks. He published 800, held out 200 as a hidden test set, put them on the so-called Kaggle platform, which is a machine learning big website that has competitions. He offered some prize money. 900 teams, but this was in 2020. 900 teams submitted programs to solve problems, and they were then tested on the hidden or private test set that they had never seen. And the winning program got about 20% accuracy. Okay. And to get that, it was allowed 3 guesses per task. Okay. So that's not great. There was some estimates of human performance, which was between somewhere, depending on the human, somewhere between 70 and 80, 90%, so something like that. Okay, so in 2024, Cholet met a very rich guy and he really liked this, and he said, well, let's give a lot more money, $600,000 for a program that exceeds 85% accuracy. And they picked the number 85 as kind of I don't know exactly how they got it, but approximately what humans should be able to do if they're trying. Okay. All right. So that's a big jump. And a bunch of teams entered this competition, and the best one got 55%. And the way that it worked was to use all of these used large language models, by the way. And the way that they used them was to first train them on the 800 published problems. It's not very much, obviously. I mean, they've already been pre-trained, but now train them further. And the way that they trained them was not to use the visual version like this, but to use a version that encoded the matrices as a matrix of numbers, where the numbers represented colors. Because if you give them the visual version, they can't deal with it. The multimodal models can't deal with that kind of thing. All right, and so they trained them on they fine-tuned them on the published version, and then then at test time, in machine learning you have training time and test time, and test time is where you give it one of the private unpublished problems. They would augment the data. They would use take the problem, and they would make a lot of related problems by flipping the symmetry, flipping things in various ways, having to do with symmetry. And they had a whole bunch of methods, and it was very expensive, but still within the limits of the competition's sort of compute limits, which they had. Okay, so this didn't quite make the prize. And in fact, there was I forgot how much, $50,000 prize for the top program, even if it didn't make the 85%. But these people, interestingly, refused the prize because they didn't want to publish their result, because they wanted to start a company to use it. Yeah.
What is the color symbol around the members?
These things,
But like blue, yeah, green, red, yeah.
yeah,
Full
Huh?
circle.
yeah, I don't remember what that means.
Okay.
I have to look it up. Yeah,
The board was increasing, so they tried many times, so.
yeah, so here in this competition, okay, there's a lot to say. I don't know if I have time.
Like 5 minutes.
Okay, in this competition, so there's like the published problems and then there's the private problems. So they didn't get to see the private problems. They got to submit their program and then the organizers tested it on the private problems. But one issue was that they got to submit their program over and over and over again. So I think they submitted their program like at least 200 times, which gives them some indirect feedback, which is like a little unfair.
Sure.
And so they're changing the way the competition works, so you can't exploit that.
So,
Yeah,
in any of these programs, use the idea that you have the copycat.
no, not at all. They all used large language models and sort of using large language models either to produce programs that could solve this or to produce just the solution.
Nothing like,
Nothing like the dynamic perceptual stuff. No, that's still, that's the stuff my group is working on. Then, okay, right after the competition was over, OpenAI released they announced their O3 system, which is a reasoning system, and they made it available to the organizers in this competition because in AI, this data set had gotten a lot of visibility. And O3 was too big to run on the server of the competition, so it didn't get to compete. But they made a special, what they called semi-private evaluation sets for it. And O3, the way that it runs is it creates different samples. So, runs several times on the same problem and then there's a vote among the different runs of what the right answer is. And you can run it different numbers of times. So here it did really well, okay, but it costs a lot of money, compute cost. And this is, I think, interesting, here at 6 samples, $200 per task. Here's how many tokens it generated. This is in its chain of thought. To do the really high cost one, it's greater than $3,000 per task. That was a lot more than we could pay our prolific subjects.
The task is one of these.
One of these, yes, yes.
Oh my God. So
Yeah.
it wrote like.
And then it wrote like 20 books. Exactly. It's insane. It's totally insane. But look, it gets 88%. But there's a lot of issues there. I'm not gonna have time to talk about some other experiments, but what is it doing in these 5.7 billion tokens? It's, you can't read it. And is it actually using the abstractions that people use when people solve them in like 20 seconds? Is it using what, Andres, did it come up with those same abstractions, or is it using some weird kind of convoluted shortcut? I don't know. Yeah, there was one in the back.
Why does it cost? Why does it cost?
Well, this is this is, they're running on these big clusters.
Virtually.
This is how much it would cost if you put your program on Microsoft Azure and ran it. Yeah. And yeah, and this is, and you won't, if you run O3, you don't see all these tokens, they don't reveal them to you, but that's how many it generated. Yeah, Martha.
I think
Oh, go ahead.
So with here at accuracy, with the cost, what about the time required?
Yeah, they didn't,
Treatments are also.
it's a lot of time. I don't know if they,
They can solve it.
Yeah, they didn't report the time, but you can imagine it took a while because of the cost and the number of tokens generated. But it was too much, the competition had a limit of time that you could take. And this was way out of that limit, so it couldn't compete.
The time is actually proportional to the number of tokens generated.
Yeah.
Gives you a bit of
A lot.
idea.
More than it, I mean, it was run on 100 tasks, and I know it took, I think the competitions was like, you could only use 12 hours of compute time
Or
for the whole 100, And it was way beyond that, yeah. Yeah, right, so they tested, this is questionable, they tested humans on a different evaluation set. And they tested them using Amazon Mechanical Turk. And I don't know how many of you have used this system, but it's not great. People, I mean, I don't know, I've used it. People often will like use machines to do the tasks for them. I don't trust it at all, but they got something like 65% on average. Yeah, yeah. So I don't know, that's still, I think somebody needs to do a very careful study of that. Any other questions? So I should stop.
Yeah, okay, then we'll move on to more general questions.
Yeah.
Are there more general questions?
Coming back to this presentation, impressed how it changed. I learned this group invariant network that you create group permutations to classify humans. If you train elements like that, under this group invariant encoding of tokens, you move in over.
If you say again,
Like we code that for deep learning for humans, there's this group invariant networks that
Yeah.
encodes all sorts of permutation of your pixels.
right,
With a transformation that's known.
yeah,
So that makes your deep learning task for image easy to detect the rotation.
yeah, so that's called the data augmentation.
Yeah, so if you would train the token like that, you
They did that,
Okay.
but you know, they do that actually, they do it more at, yeah, they do that for training, and they also do it at test time for the actual problem. They fine tune it on lots of augmentations. So yeah, absolutely, it improves it a lot. Yeah.
Another question, so there's, a lot of deep robustness papers out there, and I agree that indeed, these are things they don't work well. Performance drops, break even, go beyond the training data. They still solve this task better than, nothing. And there's also the people who say, like there's against comparers, they can only copy. I'm just thinking, where is the balance? Do you think they have some sort of reasoning capacity or like some sort of these emerging capabilities? They do, they do solve the question.
Yeah, no, I mean, that's a great question. And I do, reasoning is a little bit of a vague term, but I think my own take, and I don't have time to show some of the data from studying this, is that they are kind of a mix of memorization, what's called approximate retrieval, which is sort of trying to find something that's similar and mapping onto it. A bunch of heuristics that they are like rules that are not very general, but are specific to a particular problem type, and some general reasoning. So but figuring out what that balance is really hard.
Sounds a lot like you.
It sounds a lot like humans, but the thing is, and many people pointed this out, the fact that we have such limitations on our like working memory and all of that, is that we are forced to be more abstract than these machines, which have so much capacity for learning heuristics. Yeah.
Later question. So I was thinking, the sort of general approach is to probe the reasoning capability by searching for robustness. and failure mode. And I was thinking that humans have a lot of failure mode.
Right.
And so I was thinking of this optical illusion where you have this chessboard and you have to match the color of these things. And there humans are misled precisely because we reason.
Yeah,
We wouldn't reason.
Yeah.
We would see that the two squares are the same color, but it's our reasoning that makes us brittle.
yeah. In that case, I mean, humans are not general intelligences. We're evolved for specific kinds of things, and our visual system is evolved for the statistics of the natural world, and so we can fool it. Yeah, and so I think we have to, a lot of work has gone into what are our cognitive biases, and ours are somewhat different than AI systems, and that's sort of what we need to understand is what are ours, what are theirs, and how are they different? Let's see. Yeah,
So, thanks, Melanie, for a very nice talk. During the first part of your talk on the copycat part, this dynamic imaging between the concepts and the visual perception, I continuously come back to thinking about visual ambiguity, which is like, two interpretations that are very much steered by what's in your by the concept in your mind.
yeah,
So do these large language models actually show any kind of that type of ambiguity, which I interpret more as like, an alternative stable state system. And I was just wondering, like, whether they can also do that, or whether they show signs of that.
yeah. I don't really know the answer to that, but it's funny because they've been trained on different visual illusions, for example. And there was a funny post by a psychologist named Tamar Ullman who showed that if you the visual illusion where you have the line with the two open things and then the line with the two closed things, you say which one's longer. So he did a version of that where the two lines are the same length. He said, which one is longer? And it said, well, obviously the one with you, well, I forgot what he said. No, he did one where, no, I'm sorry. The original illusion is they're the same length, but he did one where one is obviously longer. And it said, they're obviously the same length. This is a well-known visual illusion, blah, blah, blah. And so it knows about these things, but whether it can actually perceive these things, the same way humans do, I don't know. Yeah. Why these? Why is it more difficult? Well, they haven't been trained on this kind of thing so much, although now they have. Like when I go to O3 and I give it a problem, it says, it tells me, oh, this is an arc problem, it knows about it. But I think that spatial kinds of reasoning are very limited in these models. They haven't been trained much on sort of spatial kinds of different spatial configurations. They don't have these core knowledge systems. Yeah. Yeah, that's a really good question. That's something I'd like to understand better. And, we humans have things built into our visual system that things pop out, like certain shapes and relationships between spatial relationships between things. We have these visual routines that we use. they don't have those necessarily. And that may be, you know. Cholet thinks that this data set that he created is in some sense, you know, he calls it ARC AGI now. He thinks it's sort of leading to AGI, artificial general intelligence. I'm not, you know, I think it has some special things about it. It's interesting, but it's not everything in intelligence. But I think it's like a lot of it relies on spatial perception, and these systems just don't have the right abilities for that. Yeah.
You show a chart where you compare the different GPT models.
Yeah.
3 and 4, but I noticed that the GPT-4 does worse than the GPT.
Right.
And I was wondering why, because you think that GPT-4 is better at.
Yeah. Yeah, so we found that in some cases GPT-4 and 3.5 did but worse than 3. And that may just be due to their, you know, they've been post-trained to be chatbots and to have all this sort of these avoid toxic stuff. And somehow that often can impede their performance on things. So I don't know for sure, but that's a possibility. Yeah.
I think we should maybe do further questions afterwards so that we can move on.
Yeah.
Thank you very much, Melanie.